Okay, and we're going to pick up where we left off. Last time we had proved proposition number 2, which states that every transposition can be expressed as the product of an odd number of adjacent transpositions. And we're going to move on to discuss inversions and parity. So let's get started with a definition. Let alpha be a permutation on the set 1 through n. Then alpha produces the ordering alpha of 1, alpha of 2, all the way to alpha of n. And just as a reminder, for permutations as functions, the input, right, the 1, 2, 3, all the way to n, that's the position. Okay, and the image of a number under alpha, that is the number that appears in that position. So alpha of 1, that is the number that appears in the first position. Alpha of 2, that is the number that appears in the second position. So moving on here. We say that alpha has an inversion whenever alpha of r is greater than alpha of s and r is less than s. In other words, alpha has an inversion whenever alpha of s comes after alpha of r, but alpha of r is greater than alpha of s. Okay, if for each alpha of k, p sub k is the number of terms that come after alpha of k and are smaller than alpha of k, then we may define the number of inversions of the permutation alpha to be n of that ordering of 1 through n equal to the sum of all those p's, p sub 1 plus p sub 2 plus p sub 3 plus p sub blah blah blah. Anyways, I think that this definition is easier to understand if you read it a few times, and also if given an example. So let's go ahead and discuss an example. Here it is. So the permutation 1, 2, 3, 4 has no inversions for the following reasons. After 1, there are no numbers less than 1. After 2, there are no numbers less than 2. After 3, there are no numbers less than 3. And after 4, there are no numbers, hence none less than 4. Okay. Next example. The permutation 4, 3, 2, 1 has 6 inversions for the following reasons. After 4, there are p sub 1 equal to 3 numbers less than 4. After 3, there are p sub 2 equals to 2 numbers less than 3. After 2, there is p sub 3 equal to 1 numbers less than 2. After 1, there are no numbers, hence p sub 4 is equal to 0, less than 1. Thus, there are n of 4, 3, 2, 1 equals to p1 plus p2 plus p3 plus p4, which is equal to 3 plus 2 plus 1 plus 0, equal to 6. So 6 inversions in the permutation. So basically, you just start at the beginning of the permutation and count the numbers that come after it that are less than that number, and then you move on to the next number and count the ones that come after that that are less. You add all those up, that gives you the number of inversions in the permutation. So if that makes sense, try looking back at that definition and seeing if you can make heads or tails of the definition as it's stated in the more abstract form. Okay, so here's a problem. How many inversions does the permutation 3, 4, 2, 1 have? Just go ahead and pause the video, see if you can work it out, and then we'll carry on. Okay, so I assume you paused the video and worked it out. Here we go. Here's the solution. The number of inversions is equal to 2 plus 2 plus 1 plus 0 equal to 5. So 5 inversions is what that permutation has. Okay. Now let's follow it up with another definition. The parity of alpha is defined to be even whenever the number of inversions, n of alpha 1, alpha 2, so on and so forth, is even, and odd whenever n of alpha 1, alpha 2, alpha 3, so on and so forth, is odd. Okay, so just to restate that, the parity of alpha is defined to be even whenever the number of inversions is even, and odd whenever the number of inversions is odd. Alright, moving on. Here's another example. So since the number of inversions in the permutation 1, 2, 3, 4 is equal to 0 is even, then the permutation 1, 2, 3, 4 is even. Alright? Example 2. Since the number of inversions in the permutation 4, 3, 2, 1 is equal to 6 is even, then the permutation 4, 3, 2, 1 is even. Here's a problem. What is the parity of 3, 4, 2, 1? And I'll go ahead and let you pause the video, work that out, and then come back for the solution. Ready, set, go. Okay, here's the solution. Since the number of inversions in the permutation 3, 4, 2, 1 is equal to 5 is odd, then the permutation 3, 4, 2, 1 is odd. Okay. And that's the end of this video, but next time we're going to be looking at this proposition 3, which states that given any permutation, alpha 1, alpha 2, alpha 3, so on and so forth to alpha n, if two adjacent terms are interchanged, then the parity is changed. So that's next time. We'll see you then.